getting ready now.
Okay. What we do is we try to address quantum tasks, really quantum. So, for instance, the first thing I addressed, and it worked very well, was classifying qubit states.
Mm-hmm.
You have so how we do that? I mean, and why we call it quantum machine learning. Okay, we first have a set of qubits, which all are the same, and a second set of qubits, which are also all the same,
Mm-hmm.
but we don't know the state, of course, of either set. We only know that they are the
Unique,
same.
right?
We train. Sorry.
But just
Yeah.
two unique qubits, right?
Yeah, we have say
Out of like, but yeah. Okay.
just identical qubits that are independently
Yeah.
prepared, but in the same state, in
Yeah.
one set, different
Okay.
state in the second set. So we just kind of try to devise a machine that first of all learns by measuring on these guys, on these sets, and what try to find future, sets that are going to be sent to the machine. Well, actually, you can imagine you just send just another qubit, and then the machine decides whether it goes to the set, the first set or the second set. So if the state is like, the state of the qubits in the first set or the state in the qubits in the second set. Okay, that's the idea. So it's classifying.
So,
It's
okay, so
classifying.
this is a continuation of the unambiguous discrimination?
Not
No?
not really. Because, not really. I mean, of course you could do that, but here the aim is first of all it's just it is a universal kind of machine, right? You don't know the states.
Okay, yeah.
Okay, so
I see.
you have this is like programmable discrimination, if you might remember what is it about. Right? It's exactly the same. Programmable discrimination basically is a device where you have basically two entries, two inputs. Input one is one state that you call it whatever. The input two is a different state. You don't know what you're going to be putting in there, beforehand. It's just universal in this sense. So you view as a program. These two qubits you view as a program. You view as a program, and then you fill in a third kind of qubit, which can be either of the first type or the second type, which are in the part of each. So, and then the machine just decides whether the one that is given to you is the first or the second. Okay, that's the idea.
Okay. And what's the feedback loop like? Is there? Yeah.
In this sense, okay, of course. I mean, I think I know where you. Strictly speaking, there is no such a feedback, so to say. So the machine learns by measuring these two sets of states, in the sense that it gets a classical output. This classical output goes into some classical register. Then there is a kind of a second part or second part of the machine that takes all this classical information and performs a classification for the third qubit. Okay, so basically, you're telling the machine how qubits in the set one look like, so to say, and you tell the machine how qubits in the set two look like, and then the machine kind of gets the information, classical information, keep it in a memory, and then when you send the qubit, which you don't know whether it belongs to one or the other, the machine is able to perform stuff and tell you. Okay, so but there is no feedback in this approach, really. So it's not like, I don't know, in neural networks that you really do something to the and change the weights of the different nodes.
Yeah.
No, here it's just it's optimized so that this task it's performed with highest probability of success, basically. And the amazing thing is that this machine for qubits is actually gives you the optimal performance you can have, even if if you allow yourself all sort of freedom. So if you lift up the constraints that have a classical memory and stuff, okay, you have an optimal machine that does this task, and it turns out that this particular device is optimal. And the next thing about it was that just using classical memory, so to say, classical information after the measurement on the sets, on the training sets, then by having this classical memory, you have optimal performance. Okay, so you gain nothing by using a quantum memory, so to say.
Right.
Because it has the advantage that it's a classical memory, so it does not degrade.
Yeah.
I mean, on paper, of course, the practice. but theoretically speaking, you have so you can use the machine many times to classify many future events that you will. Okay.
Any papers?
Of a state. Yeah. That's it.
Any papers that we can read?
Any papers? Sorry.
Yeah. Do you guys get to publish anything yet?
Well, this is published. This was published actually a few years ago. Yeah, a few years ago. It's okay. It's well.
Can you give like the reference or the where is PRR?
A science report of some sort, but I cannot. I don't remember exactly.
No. Whenever you have the chance, so
I will give you a chance. I think
also promote it.
Yeah, I think I sent this to Andy a couple of years ago. Andy might remember.
Maybe. Yeah, I can try to dig it up. I think so. So yeah, because I remember when you were in New York that we were talking, but back then I didn't take it. I was not as involved in machine learning back then as now. So I kind of let it go. And then recently, I've heard more and more about it. And then Gina sent me a link. So there's a class, was it like a Stanford class that they're actually doing quantum machine learning. But I haven't had a chance to actually dig into it.
Well, I mean, it can be very technical at some point, but he has clearly explained over there, so you can take a look. I think it's very clear what we're doing now.
I mean, it's supposed that we should at least be able to understand some part. If not in my case, maybe not the machine learning part, but the quantum part can work.
No, but the thing is, machine learning part is very simple because, I mean, there is no really, it's extremely simple. I mean, actually, you can completely ignore the fact that this is machine learning. You will just go through and you will see that many things you know perfectly well. It just turns out that it can be interpreted as machine learning.
Okay.
It can be interpreted this way because you first measurement on these two sets that you know exactly what they are. So you have classified for the machine a set of states, a number of states. So you have kind of teaching the machine how to do things.
What's the process of building the model like? So in classical machine learning, when we build a model, we have this standard process where you have a set of data, and then we kind of slice it into, we say, okay, this data, maybe 60% of the data, we'll use it to train the model. And then we have about 20% of the data for validation. And then we see, okay, maybe if we're not too happy with the model, we can go back and we can improve the model. And there's a third piece, which is about, again, 20%. We don't use it until we're ready, more or less, we're happy. We say that, okay, we've gone between training and validation enough times. That for in a real life case, we say that, okay, now let's see how it would perform in a real life. But then we don't go back and change it. That's about it. So I understand even if you're doing in the quantum case, even if you're doing machine learning, it doesn't have to have the feedback loop in the long run. Like once it's running, like you can maybe like, I don't know, like once you have it, you can again go back into it and maybe tweak some things. But is there like such a thing, or is there like between building the model?
The thing is so simple in this particular case that in a way you just optimize analytically what is the thing that you have to do. You don't have to play around with anything. It's just just to start with, and of course, I mean, I guess what you would say is, okay, maybe if you generalize this to more complicated situations, then all this becomes really important. You cannot really do the optimization, and you have to play around. But in this particular case, look, it's just qubits, right?
What about the experimentalists? Like, what are the experimentalists doing? Do you know?
You mean related to our work, or you mean in general? I mean,
like as far as like, is there like some implementation? And
well, actually, people in the quantum machine learning business is mostly interested in using quantum computing computers or whatever, or in fact classical machine learning. Okay. You see what I mean? It's not really that they don't really attempt to do quantum tasks.
Okay, so they're looking to bring it. That's what I meant, because that could benefit also. Like if you actually have something similar, then you could still do classical machine learning, but in
people are doing this kind of thing. I'm not really aware of what they are doing. I know that they just go in this direction. Most of them. They just want to take advantage of the quantum, complexity or whatever, just to improve on quantum machine, on classical machine learning. Okay,
but first you have some model that is like even in the state discrimination, when you're doing whether you're doing ambiguous or unambiguous, like first you're doing quantum mechanics, but then maybe like the post processing can be classical. Like once you actually decide that, like where, like once you start collecting, so maybe that part can be then classical, right?
Actually, it is usually a classical. You collect the data.
And after that, you're done.
You figure out what you're going to tell your whatever. But all this, you know perfectly well that all this post measurement stuff is somehow included in the description of what is an optimal measurement, the POVM, where it takes into account all these possible post measurement processing. So here is the same exactly. If you want me to tell you how exactly would that be implemented, a thing that we just attempted to do, and how it would be implemented, to be honest, I have no idea. I'm a theoretician.
So, that's someone else's problem.
Not my problem. That's right.
We solve the interesting things, and then someone else comes in and now please try to get some data. No, that's probably that's the reason why this will have to wait until it gets some realization in the lab, some implementation, because I think people is mostly interested in this other direction that I was telling you, but still it's getting some attention. And the field is growing fast, this quantum machine learning stuff. Where is it? What centers, like where is most of the research happening?
For instance, I know that Seth Lloyd is doing stuff like that. Probably here's the kind of maybe most advanced things. And Peter, also the guy who's going to give this edX conference. But I don't know where else. I mean, but there are a bunch of people trying this, whereas the kind of stuff that we do, still limited number of people.
Is Janusz still involved, or?
Sorry, Julianos?
Yeah. Yeah.
Not in this particular work. No, I don't think he is really. Maybe in the future he will get interested in this, but at the moment, no. He's more in the discrimination kind of stuff, and, you know.
Yeah, he loves that.
Yeah.
I mean, it's you have to know which is which, right?
Sorry.
At the end of the day, at the end of the day is what you need to know what you get, right? So that's why the discrimination comes like a very important.
Well, at the end of the day, it's always everything boils down to discrimination.
Discrimination is like, if you think of even like what the classical machine learning does. So if you're doing categorical, like if you're predicting an outcome like a yes or a no, for example, right? So I don't know if you want to predict whether a student is going to pass, like yes or no, for example, based on like certain features, and you train the model. So
that is kind of really easy.
Well, it all depends. In my case, most of them fail. Sorry.
So so you also want to know like some kind of historical data. So you want to like improve based on like, so if you know that like 80% of them on average fail, for example, like your algorithm better do that better than that, right? Because otherwise you could just say that 80% of them are gonna fail. So like actually I don't need an algorithm to tell me that.
Right. So in a way, what we're doing is something like that, but in the classical way. And what is interesting is that you know that every time you measure a system, you somehow alter the system, right?
Yeah.
So learning in the quantum world it's a tricky thing,
right?
Because interacting with your data just kind of
it's everything.
Okay. So that's why it's a completely different kind of situation. I mean, for people who do this classical machine learning using quantum resources, that is not so relevant. I mean, because they just kind of think of what they had in mind is a quantum computer, so to say, that does stuff, but gives back classical outputs, right? Whereas for us, it's important, these things, because we are dealing with quantum states. We want to classify quantum states, or we want to cluster quantum states, or whatever it is that we want to do. So okay, and that's the second thing we were attempting now. It's almost done. It's just in the stage of being written up, basically. And this time is kind of unsupervised quantum loop. So you get a bunch of qubits. Well, actually, they can be qubits. I mean, this we generalize to more complicated stage, right? And you just try to cluster these guys. So these are more or less the same. These are more or less the same. In such a way that you're carrying information. Sorry.
Okay. So that's very similar to so the unsupervised learning, basically, the way that to explain to someone who doesn't know, like the unsupervised learning, basically, it's kind of like the classic example is you bring a child in a room, for example, and you say, you can ahead of time you can tell them that, okay, anything you see in this room, like put them in 2 categories. So they could walk around, for example, maybe like put like the humans in like one group, and then maybe put like furnitures in like another group. Like that could be one way. Like if you tell them ahead of time that you're looking for 2 groups. The other one is that you don't know how many groups you're looking for.
No, of course.
Or you say, I don't know. There is no right or wrong answer. So that's when you kind of like, if it's like, again, like if it's a child going around, then like maybe they could just look into shapes. Maybe like they could put the electronics, for example, in like one group, and maybe like some other like clothes into like another group, and then maybe like the humans still in another group, and kind of like, so basically, and then the human like still has to like look in, or like someone like, as an expert has to look in, and first to actually label the groups, because ahead of time they don't have labels. You don't know what they are, right?
Well, in the quantum example that we are considering, there are only two kind of possible states again.
Right.
It's just, you have to start with a very simple.
Yeah, but you don't know, right? So like you still have to, let's say you cluster them into groups.
Well, let me explain what this thing about more precisely, maybe you. So the thing is that you get a sequence of states. Now these states can be of two kinds, but you don't know specifically what are the states.
Right. Okay, yeah.
You only know that there are two different kinds of states.
Yeah.
Are they orthogonal?
No. If they were orthogonal, then it's trivial.
Okay.
Then in this particular case, it would be
simple, right?
It would be like distinguishing 0 and 1 in a long sequence. So it's not a big deal. But here you get all these states in a sequence, and you don't know whether it's a state 1, 1, 2, 2, 2, 2, 1, or what are, you just have to take out of the sequence those that are type 1, put them in one cluster, and those who are type 2 in a different cluster. You don't know. That's the interesting thing. Actually, the exact description of the state.
Then it's exactly basically it's like similar to what we do in the classical world. Like you don't know, like you still have to like look in, but then at some point do you then
freezes a little bit. That's what you're doing in the classical, you said.
Yeah, pretty much. But then at some point, so then do you do discrimination after that, or you're not interested?
Well, you could always see these tasks as a kind of discrimination, because you could imagine the whole sequence has a quantum state. The sequence like a quantum state. If the sequence has a different kind of clustering, or belongs to a different kind of cluster, it will have a different, of course, quantum state. So you are actually discriminating between all these possibilities. So it's always discrimination at the end. Okay, that's
discrimination.
Everything ends up being discrimination if you think about it. Okay,
but you don't, in discrimination, like you would know if it's psi 1 or psi 2, right? You would know at the end of the day once you perform. But in this case, in this case,
you just pick labels, so to say, these are 1 and these are 2.
I guess it doesn't matter. Okay.
It doesn't matter whether you're doing just clustering. Those guys here, we believe are in the same state. Those guys over there, we believe are in the same.
Doesn't matter.
But you don't know how many are in each cluster. It could be. We only know that there are 2. Of a state.
And what do you use? What kind of metric do you use to optimize those clusters? So like in classical.
We perform a collective measurement. It's the only way we can do it in the quantum world, right? You have to perform a measurement at some point to learn.
Right.
And the nice thing about it is that it has to do with all the. You might remember that when you have, of course, many qubits, you can use SUN techniques, representation techniques, and take the states, decompose the states in irreducible representations, and all that stuff, right? Group theory. That's what we're using, basically. We're using group theory, and if you remember group theory, there's actually a kind of factorization where you have say a product of two. The states classify in such a way that there's how would I say, like a tensor product of two parts. One that has to do with symmetries, with a symmetric group, okay, and the other one that has to do, okay, with say the whatever is not there, what is really the group theory, SUN. So you have this kind of factorization, and the nice thing is that you only have to measure in one of these factors, the one that has to do with the symmetric group, the permutation group, right? So in a way, there is a lot of information that's still there after classification, and this is very, very interesting, because I mean, if by classifying these states you would kill completely the information that is contained in them, that wouldn't be really very, very exciting. I mean, it would be still a challenge, because they are quantum states, so that's so easy to classify, but it would be pretty useless. Now, what we have not really studied this part, but it's obvious that there is a lot of information still left in the states. So in a second stage, what we want to do is kind of, well, quantify this information and see whether we have some particular situation where this can be useful.
Yeah.
And we will find them. You know, it's almost for sure that there will be such a situation.
Okay. So a lot of techniques so when I first started doing, especially unsupervised learning, I kept on going back to a lot of the things that we were doing in quantum mechanics. So a lot of it comes like the processing, like how you organize the data that you have. Like data is very often very messy when we're given a data, like turning that, like the hardest part is like kind of like figuring out how to turn all of these things into vectors. Actually, if you like, even though you haven't done like regular like clustering, but like if you were to look into, once the data is processed, then it's basically, as a physicist, like you have no problem doing clustering on that.
Yeah, it's a big vector.
Like you have a bunch of vectors, and then you can choose like, okay, what metric do I want to use to group these into two? So like one of them can be like inner products, for example. You can see like, okay, like I want to see like if these things have like close inner products, they could be in one. And then if they have like something else, then whatever cutoff, then you put them in another group. So basically, like once you, like everything kind of like turns into just turning things into like a series of vectors. And then any kind of metrics, like inner products usually work quite well. And so kind of you live in a very highly dimensional space. That's the only like every vector. So for example, if you have information on like students, so it could have like age, like where did they go to school before this, and like other classes that they've taken. And then you give them weights, you normalize all of the vectors. And after that, you're kind of doing like the same thing.
Yeah. It's very,
I was puzzled that it was called, like I didn't know that it had a name. Like that's why like, so you're kind of right though, because like we were always doing these things, but in computer science, they call things machine learning that we maybe called it linear algebra and building models.
Well, it always, everything boils down to the same stuff at the end of the day, with a different name and a different
It's always like a bunch of basically a series of vectors and a lot of inner products, and then figuring out okay, like what you're optimizing from there on.
I agree. And once you know a little bit of well, the techniques that we just learned doing, you doing your PhD and doing her PhD and so on, all these techniques are very useful for all.
They're the same. Yeah, I remember like we had so many discussions where we're like, I'm trying to figure out, because I started learning machine learning from like a more traditional, like more from someone who has a computer science or statistics background, and but there's a tendency to jump into like all of this terminology very quickly.
Yes.
Like even like neural networks, like they come up with very fancy names, but there's nothing fancy actually. Like once you go down to it, it's basically like all you do is just like you have a lot of vectors, and then from there on, you just basically it's all the same. So in that case, I was very happy when I first realized that okay, I actually know this. I just didn't know what to call it.
That's right. You just have to stick a name.
That like okay, so then we'll just call this. This will be supervised. Supervised.
But of course, this is we always, our problem, I think, as a theoretical physicist, so to say, is that it takes I mean, we tend to solve problems analytically, so to say. We always have to optimize things as much as we can. We get to get the maximum, maximal performance of everything, and it has to be done in an analytical way. Otherwise, we feel kind of And of course, in the real world, this is useless. I mean, what you have to do, first of all, the optimal performance of something. I mean, nobody really cares. In a way. It's just a device that does a job in a reasonable way. Of course, improving.
You want to get an idea like how well it does, and then you still have to go back and do some other optimization.
Yeah, and most of the time it's just numerics that you're doing. That's I think our limitation. We know a lot of the stuff, but when we go into the real world, we somehow, at least this is my case, I kind of get a little bit scared by all these numerics and stuff because I'm not used to that. I just want to solve the optimal problem because I want to learn something. And this is
that's always the hardest part. The numerics is like usually a little bit easier than the analytical.
Yeah, it is. Well, I don't know. It all depends on how well trained you are.
Yeah, I mean, you do have to add some more tools to it. Maybe just like learning like a few other things to improve on the numerics. But I still find, like, even now, I still find the analytical part to be the hardest. This is maybe we have that, and then the other extreme, I think, from the maybe like more on the practitioner's point of view, is that they very quickly jump into optimizing numerical models, but then it's kind of like the same thing where you're over optimizing things, but you don't have a deep understanding of your models. And then when you start implementing them, you kind of like start reaching those boundaries. So
I don't know. To be honest, you know better than me the answer.
The only thing is that you're kind of.
I don't know.
Yeah, but you're closer.
We don't have. Sorry. Finish what you said.
Yeah, but the only thing is that we are much closer to reality, so we are forced to check with reality very quickly.
Yeah.
That's usually the feedback loop.
Yeah, because we can just ignore that for a while.
Doesn't matter. You can keep going.
No, I mean that sounds very shallow. No, I mean, but I think we are doing serious work. But it's true that the implementations of all this stuff for a very theoretical kind of guy as I am, or other people who's working, collaborating with me, this is not our main concern. This is
maybe that's where we can come in at some point. So actually, that should be interesting to see, to take it from what you guys are doing now, from the analytical point, and then to see what can we bring in from the data science perspective. Like to see, like, do these other tools that we are actually using and implementing, like, is there some value in there?
I'm sure.
Value. Like, I think that would be very interesting to see.
It would be, no, for sure. I mean, as we tackle more complicated problems, eventually we will need to know numerical techniques, and probably would bring a lot of useful techniques and so on and so forth. At the stage we are now, we're dealing with the most simplest tasks in the quantum world and the simplest system. So, but of course, the idea is to try to do something more interesting from the practical point of view.
So maybe we can leave it at that. So maybe that could be the thing.
Yeah,
we can see. So we can talk. We can have another call, but just to see where, like, I wouldn't mind getting more technical on another call, but just to see like where you guys are, and then I want to see like what we can bring in from in the numerical spectrum, and maybe publish a paper.
Yeah, well, that would be nice. It would be nice. We have to. Well, we have to think very hard to maybe you should do a kind of brainstorming.
Yeah, of course.
I don't know exactly. I mean, there are interesting directions, I guess, but I don't know. It would be nice to find something that would have kind of immediate or application in the quantum technologies. I mean, this is the aspect that I'm interested in. I mean, it's clear. Right? I don't want to do classical machine learning.
Yeah.
I want to do quantum machine learning in the sense that I want to do quantum tasks.
Yeah.
So we have to think about situations where, things that are useful for quantum technologies,
yeah.
and for which, all this quantum machine learning, the way we understand or the way we can be useful, we have to think about it. I don't really don't at this stage know very well which direction all
We can
this.
look into, maybe that's what we can do on our side, to look more on the commercial space, like what is commerciable.
Oh,
Like not exactly. No, not exactly like directly commercial, but like there is still like interest right now. I'd say mostly from like the governments, like primarily, and mostly from a security perspective. And maybe we can see, maybe we can figure out a way to then merge this.
Yeah, I don't know whether in this context, I'm pretty sure that machine learning could say a lot if we think about it carefully. We never our work or our way of making progress is slightly orthogonal to that. We just don't care about, but you know what I mean. We don't care, of course, that we would have something that is useful immediately for some commercial application, but we are more interested in kind of very fundamental questions.
Yeah.
So we just learn to do it.
Yeah, maybe we can make the money then. You guys do the work and we'll make the money.
I'm feeling we are losing a collaborator right now. So somehow I feel that he's not going to answer anymore to us for a while.
No, we'll sponsor his business trips or his academic trips.
Yeah.
Well, I don't know.
Emili loves New York, so we can.
I don't know. I mean, no, but it's interesting to maybe. I hope that I could visit New York in the near future. I wish Gina was also there, of course.
Yeah, there's a big storm right now, so like we're not in the middle of a very, very big winter storm.
Yeah. Oh wow! I mean, it can be very bad. I know.
I'm kind of looking for it, but I ordered some fried chicken and then I had some bourbon.
You both guys at home now or what?
Yes.
At home, okay. So it's pretty late, right? There, what is it?
Yeah.
Oh, 9. It's 9 o'clock.
So what is
an hour less.
What is it?
Oh, an hour less. It's 8 in your place.
Yeah.
Okay. Well, here it's very early. It's 10 in the morning.
No, we're sorry about that.
No. I woke up pretty early, to be honest. I was up 6:30 or something. I was too hungry to sleep.
It happens to me too.
Yeah. So my first idea was, well, I would do some exercise, but then I was lazy and I went directly to the canteen. And had some.
You can do exercise on an empty stomach.
But now maybe, no, I won't do it. No, I have things to do. But anyway, I don't know. I started exercising again, which is good because I was gaining weight. So complete disaster, my friends.
So yeah, thank you so much, Gina. Do you have any more questions? You good?
No, I think so far I'm good. Actually, I need to read the paper.
I want to.
Yeah, I will give you the link. Yeah.
Because yes, because for example, I was thinking about at some point you will, but we can discuss it in another time. Like at some point you will have like a threshold that you cannot, you have to stop the threshold for optimization, right? Like happens in the unambiguous state discrimination and the minimum error, where you cannot go beyond that threshold because of the quantumness of the system.
Yeah,
even if you are using, for example, classical machine learning to do the separation or the classification, eventually there is no more than you can do because of the quantumness of the system. It's not like a statement, it's more like a question. Like the classical part will be like cut or bounded to the quantumness of the systems that you're studying. For example, it's one of the questions that I could raise now, but I would like to read first the paper in order to probably clarify more the question, no?
Yeah, no, I would say that this is taken into account, of course, in the paper. When we say we optimize, it's of course in quantum mechanics. So the limits are set by quantum mechanics. What is optimal? Yeah. So I said that our machine learning or quantum machine learning protocol, it's optimal in the sense that if you want to be as general as nature allows you to be, you're not going to do better than this protocol. So it's optimal in this sense. And this is pretty interesting because it's not obvious at all, because you have this classical memory. So why in hell the fact that you're having a classical memory does not somehow,
the optimization, right? Give you an advantage over the quantumness of the system that is the one that is bounding you. I'm guessing.
So, no, in this case, there is no restriction that is imposed at all. And actually, it's extremely good because then you can use the machine again. So once you have trained the machine, all the relevant information is a classical memory. You just do again and again, the same task until of course you change your training set. I mean, the training set is
you change the two states that you're working on. Yeah.
If you change the training set, then of course you have to feed into the classical memory. That's the idea, basically. Yeah. I don't know. I could imagine a situation where you have a device that is kind of producing states, but of two types. You want to produce, say, type 1, but there are some errors, and maybe once in a while you're producing type 2 or whatever. I don't know, right? So you could train your device with a few of these produced states, and once you have trained the device, all the information is in classical memory. So now you can use your device to classify future states which get out of the, got produced with the source. Of course, if the source changes, you have to train your device again. I mean,
you have to start all over again.
Well, that's very interesting, though. That's very interesting that actually, so now I understand the importance of it. So like once you train the model, once you train the algorithm, but like everything, like the memory is then classical, so then you can use it like later on. Actually, that's a huge advantage.
Yeah. Well, that's the nice thing about this paper. I mean, if this classical memory wouldn't, have been optimal, then, well, I mean, still, I think it's interesting because, again, as I said, we are so obsessed about optimality that if we just find out that using classical memories, this is not optimal, we would have killed ourselves. And maybe it's a stupid thing. Well, I'm sure it's a stupid thing to do. Maybe it's just a stupid thing to do because even though it's not optimal, maybe it can still be useful.
Yeah.
Right? And that's the kind of mentality that we have to change. We just always obsessed by optimality and blah 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 blah. And that's not the real world is after, basically. They want to have good solutions to complicated problems, but they don't care whether it's the optimal one.
No. Very often it's good enough, and then it depends on the kind of problem that you're solving. So if you're in medicine and you're producing some kind of a drug, then you want it to be as optimal as possible.
Of course. I mean,
if you're in the business world and you're trying to predict, okay, how likely is it that this person is going to buy something from me, then you just want to have a good idea, but it's not going to kill your business, basically. Like,
of course. I mean, that's the point. I mean, provided it
like the problems that you solve. Yeah.
That's why it works, right? Yeah, I agree. But even in medicine or things like that, I mean, if you improve on something that it's
right,
a market, you improve on that. I think that's already important. Even if you're not really, being optimal, you don't know many times what is the solution for everyone. It's very hard, right? I mean, that's the thing. So if you keep improving something, you're doing well. We have to somehow adopt this mentality. We're still kind of in this more academic world, where optimality is the
I want all of it.
Yeah, well,
information in this box.
the derivative with respect to the parameter equals 0. And then, well, that's the one.
Okay. Well, Emilio, thank you so much.
You're welcome. It was very nice seeing you.
I know. We haven't seen each other.
You look very different.
It's been like 2 years, I think, right?
Really?
You look very different.
Is that good or bad?
No. It's good. You look gorgeous. Believe me. So.
Yeah, we haven't seen each other. I don't know, probably like what, 5 or 6 years, something like that. I don't remember. Probably 2012, 2012, 13 in New York. Yeah.
Long time ago. Yeah, like more than 5 years. So I really would like to to meet again.
Yeah. No, don't worry. We're gonna be bothering you very often.
Okay. Well, I wish I could, be of more help, but I'm afraid I'm very kind of limited in this area still.
No,
maybe.
I actually think it was very, very enlightening in the sense of like a first approach to the topic, because it sounds, when I saw this ad that I sent to Andy, I was like, what is it? I mean, it's like, are you serious? I mean, I'm beginning to learn machine learning, right? And they already put the quantum, and I'm a quantum physicist, right? But I was like, wait a second, what is it? No, then that's what the idea became about talking about this with you, and he remembered that you were working with these things. But it is crazy because actually I was talking to some friends like, oh, we're gonna have this interview with Emili and about quantum machine learning, and everybody was like, are you kidding me?
What is this?
Yeah, what is this? And mostly they are coming also from quantum physics or atomic physics. So I said, I don't know, I'm gonna find out. So now it's kind of pretty simple. Like for me, like one of the main ideas that I see is kind of like two parts that are running now related to quantum machine learning, that is using quantum systems or perform measurements and things on quantum systems and use machine learning in order to optimize the process, the quantum process.
Well, this can be also another possibility, but that's not the one that we're really after. I think that the two main branches, so to say, that this is taking, one is quantum machine learning to make really quantum tasks, to solve quantum tasks. You're dealing with quantum systems, and this is your world. So you don't. And then the other one is you're using quantum systems to improve on classical machine learning. I would say that these are the main two situations. I'm sure that there are people who is also doing what you suggest, because it's true. I mean, there are quantum tests that maybe, you have to do some optimization of some sort, or you have to do, maybe, having a classical quantum learning machine protocol will help you. But of that, I'm not so aware, to be honest. Well, actually, I'm not aware of any of these things.
No, but for example, what you're saying now, I think it's really important, because then you clarified like the idea of what is going on, right? For most of the people out there, like, or people
variations of, I mean, you could be more precise, but to be, by the way, you know Gael? Do you remember Gael? Did you ever met
so.
Gael Santis in the UAB in Barcelona?
I don't remember now.
With a lot of hair, not like me.
But I don't remember right now.
Okay, he knows a lot about that. That's one of our collaborators, and so maybe you would like to talk to him. I mean,
that would be nice. I don't know if you have the chance to send the contact information so I can contact him. I really don't have a a face right now. Probably I met him while I was there.
From Tenerife, well, from Canarias. I'm not sure whether Tenerife or somewhere.
No, I don't remember.
No, not a ring. Doesn't ring any bell. Yeah. Okay. Well, it doesn't matter. I can give you the contact if you wish. He knows a lot more. He's really into this business. heavily. I'm now and then, doing some work on that, but also working many other things. So this is just part of my research, which just happens to actually now be very active because I'm finishing with him and with Ramon and John, which you might remember. Another paper about clustering. Okay. So maybe next time I will be able to explain more things because I have to go through again the paper. So brush a little bit my memory, because this is something that we did like maybe more than 2 years ago. But then it just stood there for a while, sitting on the table. Nobody was really doing anything about it. Since maybe a month ago or so, Gael visited us and we started working on that again. We did some improvement on we produced new results, more general results, and then we thought, okay, we have to do it now. So we are kind of, in this situation. We're just writing things up. There is a first version of the paper. And now I should have read this over the Christmas holiday, but I didn't because I didn't have the time. I had other obligations, among other things, pay attention to my family because I was going to be for a long time. So I felt obliged to, and now I have to do it. And the trouble now is that I'm teaching this course here in Hong Kong, and it's draining all my energies basically.
Which course are you teaching?
I'm teaching quantum information here, but this is a computer science department. So it's mostly, a big chunk of it is, quantum complexity and all that stuff, which I don't know that much. I know something, but I have to, again, brush my memory on many things here. Okay, and there are also, of course, the standard content of quantum information, teleportation and then coding and all that stuff. It's also in the course, but I got here like more than 40 students, and some of them are very clever. To be honest, the questions I got the very first 2 days of the course. Well, some of them took me a while to figure out how to.
But that is great. When you're teaching, that is great. When you are like,
it is. No, it's fun.
It's
a lot of fun. I was actually preparing exercises when we started talking, and I'm doing that. A lot of excitement because I know that some of them are going to really appreciate, if I give them good exercises. But still the number is limited of these very, very clever guys. Usually it's not more than 10% of the class, but it is worth, is this 10%, you just kind of focus on them and you kind of get excited.
Let me know, maybe we can hire them later.
Maybe. Yeah, because this guy is a computer scientist.
Yes. Oh yeah, that would be great. Actually, we need some computer scientists. If they can do computer scientists who can do quantum information theory, like that's.
I don't know. Some of them are so clever that they could definitely do some work on that.
Yeah.
But still, what I say, you have to take it.
PhD level or is it masters? PhD.
Sorry, undergrad.
Undergrad. Okay.
But pretty advanced undergrad, so
Okay.
Third year, or I don't know.
Okay. So let's stop then. So maybe the next one can be on teleportation. I think that one is.
Teleportation. That would be nice. Okay. Well, nice guys talking to you.
Gina.
What?
Yeah.